This video picks up where the previous discussion about the MOS threshold voltage concluded. We assume that we know how to determine the MOS threshold voltage, and this video examines how the resulting channel responds to changes in gate-to-source and drain-to-source voltages. So, we consider four cases: A, B, C, and D. In each of these four cases, we have a gate-to-source voltage greater than the threshold voltage. The cases consider a N-channel MOSFET, an NMOS or NFET, with a lightly doped P-type substrate, heavily doped N-type source, N-type drain, insulating layer above the channel, and the gate electrode, to which we have applied a gate-to-source voltage greater than the threshold voltage Vt. The channel length has a length L. We define directions X vertical, Y from source to drain, and Z into the plane of the drawing. The first two cases, A and B, describe the transistor operating in the linear or triode region. Cases C and D describe the transistor operating in saturation, also called pinch-off region. So let's consider how these four cases work. So case number one, case A, we have 0 volts applied to the source in all four cases. We have 0 volts on the drain in case A. We have a conducting channel present with the gate-to-source voltage above the threshold voltage. In addition, we have a depletion region formed under the N-type source, the channel, and the N-type drain. The depletion region has the same width under the source as under the drain because the drain and source have the same potential difference to the body. Zero bias if we assume the body connection sits at 0 volts. So that case doesn't surprise anybody because if we view the channel as behaving as some kind of resistance, then 0 voltage across that resistance, 0 VDS, causes no current flow. If we increase the drain voltage slightly, so VDS greater than 0 because of VD greater than 0, then we send the drain to body junction, this PN junction, into, and I'll ask you to think of whether it is forward or reverse bias. We apply a positive voltage on the N-type source. In fact, pause the video to think about it before continuing. If we apply a positive voltage to the N-type source and a more negative voltage to the body, we reverse bias the PN junction and widen the depletion layer width. So if you look really carefully, you'll see the depletion layer between the drain and the body looks a little wider than the depletion layer between the source and the body. Subtle effect also happens as we apply, first an obvious effect and then a subtle effect. If we apply drain voltage greater than 0 to the drain relative to the source, we expect electrons to flow toward the drain. The positive voltage attracts electrons. We get current flow in the channel, so a non-zero current should flow. Also, and this is the subtle part, with the positive drain voltage, we suck some of the electrons out of the drain end of the channel, thereby slightly reducing the electron concentration on the drain end of the channel relative to the rest of the channel. It's only a slight change in electron concentration difference, and I try to indicate it by drawing the curve on that blue line a little bit. Okay, so if we compare the current in case A and B, we should have a greater current in B than in A. We can plot that on a current voltage characteristic shown on the next page. We plot the drain current versus the drain to source voltage in case A. 0 volts VDS gives us 0 current. Positive VDS in case B gives us positive current. The channel continues to behave like a resistor with a roughly linear current voltage characteristic between points A and B. What's going on as we increase the voltage even further? You notice between B and C, the current continues to increase as we remain in the linear mode, but once we reach what's called the pinch-off point at point C, the transistor saturates or pinches off, depending on which nomenclature you use. We call linear the linear mode or triode mode. We call this region above at higher VDS than point C the pinch-off or saturation region of operation. The current remains roughly constant in the transistor between points C and D. Let's see how that happens in the cross-sectional pictures. Case C, we still have same VGS greater than VT applied, so we have a conducting channel. We apply a drain voltage equal to the pinch-off voltage, also called the overvoltage by some authors, called the edge of saturation voltage by other authors. Either way, we apply a voltage to the drain equal to the gate to source voltage minus the threshold voltage. Notice what that means. If the drain to source voltage equals the gate to source voltage minus the threshold voltage, then the voltage between the gate and the drain just equals the threshold voltage, and we reach the threshold condition right at the drain end of the channel. So remember, the threshold condition happens when the channel carrier concentration just equals the bulk carrier concentration. In other words, we've just inverted the electrostatic potential in the channel compared to the bulk value. So the threshold condition means that we should have a lower electron concentration at the drain end of the channel. Right at that point, we say the channel has pinched off relative to the higher electron concentration or carrier concentration in the rest of the channel. The drain to source voltage in case C exceeds the drain to source voltage in case B, so we also expect a more reverse biased body to drain diode and therefore a wider depletion region on the drain end of the transistor. This pinch-off point represents kind of a point of maximum current. If our current gets limited by the electron's ability to squeeze through this pinch-off point, and I'm doing some hand waving in my language here, but it's not horrendously misleading. If you want to get a better picture of what goes on, you actually have to get involved in solving the Poisson equation in 2 dimensions minimum, and that gets to be a lot of fun, but that we will leave to more advanced coursework. But what happens if we increase the drain to source voltage above this pinch-off voltage or overvoltage? Then, well, we continue the process. The depletion region between the body and drain continues to widen. We continue to suck electrons out of the channel region. And instead of the depletion region the pinch-off point just occurring right at the drain end of the channel, because we have a higher drain voltage sucking more electrons out, the pinch-off point retreats away from the drain toward the source. Another way to describe that is that we have a transistor whose channel we can represent with a resistance has a shorter length in case D than in case C. And as you know, if we take a region of semiconductor and with these two regions have comparable electron concentrations, but the case D channel extends shorter, less distance than the case C channel, then we have a shorter channel in case D than in case C, and we have a lower resistance channel in case C than in case D. So we have, by this delta L difference in channel length, and delta L is typically a pretty small number, small fraction of the total channel length for many high-quality transistors even, typically less than 5% of the channel length, then we see less than a 5% increase in current from case C to case D. If we look at that in the current voltage characteristic, the current remains roughly constant between case C and case D. And one way to see that is because the pinch-off point happens at the channel location where we reach the threshold condition. So the voltage on the end of the channel in case D equals the voltage on the end of the channel in case C. But then we have this additional voltage drop to get from the case C voltage, pinch-off voltage, up to the total VDS. This becomes more clear, perhaps, if we look at the plot of potential versus position in each of these 4 cases. So in case A, this plot shows potential on the vertical scale versus position, source on the left, drain on the right. In case A, we have 0 drain voltage, no potential anywhere. Case B, we have a slight drain potential, and the channel behaves like a resistance with a roughly linear potential drop along the channel. And when I say linear potential drop behaving like a resistor, It is also true that the channel behaves like a resistor following Ohm's law, but this plot does not show you Ohm's law. This plot plots channel voltage as a function of position versus position. In case C, we reach the pinch-off condition. We obtain an overvoltage equal to VGS minus VT at the drain. The channel behaves like a resistor with a linear potential drop. Case A, B, C show increasing current. Look on the current voltage characteristic. Current increases from A to B to C. Higher to lower, 0. Going from case C to D is the interesting one. So we increase the voltage on the drain, pushing the pinch-off point away from the drain to this location L minus delta L. But we still have a potential drop from the end of the channel out to the drain. Well, as you know from your study of p-n junctions, okay, so we have the same potential at the end of the channel in case D as we do in case C, but in case C, the end of the channel occurs at the drain. In case D, the pinch-off point gets pushed away from the drain. But we still have potential dropping from the pinch-off point to the drain. This region has very low or no carrier electrons in it. So we call this we approximate this as a depletion region. Really, it is a depletion region. If you look at the cross-section of the device, we have nice conducting carriers in the channel and then depletion region from the pinch-off point to the drain. As you know, to obtain the potential distribution in a depletion region, we integrate the charge. It's space charge due to the substrate doping, p-type acceptors in this case, for an n-channel FET. And we have the integral of the constant charge gives us a straight E-field distribution. Integrate this straight E-field gives us a parabolic potential drop from drain to the pinch-off point. So we have that parabola there to drop all the extra field. And I should point out that the steep potential drop means a high electric field on the drain end of the device. And this does correspond to a place where the devices can break down. If the E-field goes too high, we can get a breakdown happening in the transistor, and deleterious factors happen there. If you're interested in talking about this in more detail, I'm happy to talk about it because not only is it interesting, but I also spent a summer as an undergraduate working at Xerox Palo Alto Research Center, studying, among other things, the electric field distribution on the drain end of the channel and figuring out ways to mitigate the electric field to avoid breakdown in these devices. And I think you'll figure out right away that one strategy that people employed back then, and some folks still use the same strategy today, and even in integrated circuits, but also in high-power devices, is to reduce the doping at the drain end of the channel to reduce the peak electric field there. But we'll not worry about that right now. Okay, so this gives you an overview of what's going on. Now we go do the math. You ready for math?